Alright, so in this video we're going to be talking about rational expressions, or in more specifically, we're going to be talking about how to simplify rational expressions. So when we talk about rational expressions, we're basically talking about the quotient of two polynomials. And so below here we have an example where it's x plus 6 all over x squared plus 5x minus 6. So those are two polynomials that are in a quotient or are divided by each other. Okay, so we're going to start with a pretty simple rational expression here. So we have numbers and a variable, but we don't have more than one term here. We just have a coefficient and one variable on each of these. So when we solve for ones like these, we first of all want to deal with the numbers, so the coefficients of those variables. And then second of all, we want to deal with the variables themselves. Okay, so let's do step number one. We're going to deal with the numbers. Well, if we take a 4 off of 16 here, so if we want to divide this by 4, okay, well, that's just going to give us, in our next line, we have a 4 there, right? Because 16 divided by 4 is just 4. And then what if we divide that same bottom term by 4, then we would say that this one is going to be 7, because 28 divided by 4 is just going to be 7. Perfect. So now we've dealt with step number one, we've dealt with the numbers. Now we want to deal with the variables. So in this case, we have two variables over each other or divided by each other. So when we divide variables, what we have to do is subtract their exponents. So let's just write that as a note off to the side here. When we divide variables, then we must subtract the exponents. So in this case, if we have let's write it here, p squared over a p, that technically means that we're going to say the exponent in the top side, 2, and then the exponent on the bottom, well, p is just p to the 1. So we would say minus 1. And if we say p2 minus 1, that's just p, because that's just going to be a 1 there technically if we want to write that in. So now we know that in the numerator, we just have a single p left over. And therefore, that's our simplified rational expression here. Okay, we have an example that's pretty much like the first one. It's just another one for practice here. So we have 15n over 30n cubed. So if we deal with the numbers first, we're going to say 15 over 30. Well, that's just equal to 1/2. And then our second step, we want to deal with the variables. And we have an n over an n cubed. So n over n cubed, remember, if we're dividing variables, we're subtracting their exponents. So this is equal to n to the 1 minus 3, which is equal to n to the negative 2. And any variable to the negative just means that we have its inverse. So we can say 1 over n squared is our result. Okay, so now we know that our n is in the denominator here. And then, therefore, this is our simplified rational expression. Okay, so for our next example here, instead of dealing with just single terms of numbers and a variable, now we have to consider the rational expression and say, what can we factor out of this rational expression to make this work? So when I look at all three of these terms, they share a common 3 with them. So when I look to this, I say, well, if I pull a 3 out of this, so if I say this is equal to, and we pull a 3 out of both the numerator and denominator, then what does my inner term become? Well, 15 divided by 3 is just going to be equal to 5. We keep the a there. Minus, what's 3 divided by 3? Well, that's just 1. And then all over, what's 24 divided by 3? Well, that's just 6. Or sorry, that's just 8. What am I talking about? So now we have this here. So that's our simplified term. We know that a 3 over 3, because we pulled out the 3 from both the numerator and denominator, these we don't actually have to even write again in our next step. We can actually just leave those behind now, because 3 over 3 is just 1. So we have just 5a minus 1 over 8. And can we do anything more to this? No, because there's nothing more we can simplify here, both in the numbers and variables. So we know that this becomes our final solution to our simplified rational expression. Okay, and similarly with this example, now we just have the more complex rational expression, or the more complex polynomial in the denominator. So when we deal with this one, now we have to consider the same type of technique. We have to say, what can be pulled off of all three of these terms to make this work? So when we try and take a term off of all of these ones, well, what can we take off of all of them? I would say a 9 would come off of all these and be the greatest common factor for these. So if we take a 9 off the numerator and denominator, we're going to be left with, well, 27 divided by 9 is just 3, over, well, we have that same 9 off of a 27, which is this 3, but we have to keep the x there. And then we say 9 off of 18 is just 2. Perfect. And then in our final step here, we say, well, 9 over 9 is just 1, so we don't have to write that again. And we just have 3 over 3x plus 2. And can we do anything more to this? I don't think so, because we can't do anything with the numbers or the variables in this case. And we can't just cancel off the 3 from both the numerator and denominator on these two terms. So let's say we consider this one and this one. We can't just divide the 3's there and say that they cancel the 1 because it's attached to this 2 here. So we know that this is our last step here, and this is our simplified rational expression. Okay, for question 5, now we're going to deal with factoring to simplify, which was that third type of problem that we're going to be dealing with. So when we factor to get these, let's just do them independently. Let's do the numerator first and then the denominator, and then we can sub those factored terms in for the answer to see if we can simplify. So what I mean by that is let's just deal with the numerator first in this case. So we have x squared plus 8x plus 12. And then, so to factor this, what we need to do is get a term that multiplies to make the product of the outside. So 1 times 12 is just 12. And then adds to make the middle term, which is just 8. And so in this case, what I would say is those numbers are 6 and 2. Because 6 times 2 equals 12, and 6 plus 2 is equals to 8. And then we need to look at one more thing. We don't have to do decomposition as long as this term here is just 1. So if that term is just 1, then we know that 6 and 2 are the factors of our problem, meaning that we can just say x plus 6 and x plus 2 are the two factors. What about our next one here? So in our denominator, we had x squared plus 3x minus 18. Okay, so what's going to multiply to make the outside, which is negative 18, and add to make the inside, which is just 3. Well, what I would say in this case is I would say if we need to get a negative here, then let's put this as negative 6, and let's put this one okay, so we need something that's going to multiply to make negative 18. If we need something that multiplies to make negative 18 and adds to make negative or positive 3, then we know that this 6 would make sense here, and a negative 3 would make sense here. Because 6 times negative 3 is going to be negative 18, but 6 plus a negative 3 is going to give us a 3. So now we can actually just write those again because we don't need decomposition. Because of our single term in the front there, we have a 1 as the coefficient of x squared. We know that our factors are just x plus 6 and x minus 3. So now our second step comes over here when we replug those back in for our original equation. We've solved for the factors of both of them, so now our new equation looks like x plus 6 with x plus 2 over our second one, which was x plus 6 and x minus 3. Okay, so now we have our factored terms that we solve for. Let's just simplify this by canceling the like terms. In this case, we see that an x plus 6 and an x plus 6 are both in the numerator and denominator, but I don't think we can cancel anything else from there because no other terms are common than that. So we would say that this is going to be equal to x plus 2 over x minus 3, and that's our final solution as a simplified rational expression. Okay, so now we have a problem that involves factoring and taking out some of the terms or the greatest common factors. So it kind of combines our third and fourth problems and then puts them with the last problem we just did. So step one, let's try and factor some stuff out of both the numerator and denominator such that we get a more simplified term before we can actually create the general factors. So what can come off of, in the numerator, we have 9x squared plus 81x. What can we take off of both of these two terms? Well, we can take off a 9 and an x. So if we take a 9 off and an x off, then we get just a single x left over, plus, well, what's 9 off of 81? That's just going to be 9 itself. And if we take off the x with it, then we're just left with x plus 9. Okay, and then for our second one, we say, or for our denominator, we have x cubed plus 8x squared minus 9x. Well, it looks like we can take at least one x off of each of these, right? So we'll take x off of each of these terms, x minus 9. And then now we should recognize this one from our last problem. We need to factor this such that we can try to simplify both the numerator and denominator. So if we go and say that now we're dealing with the x squared plus 8x minus 9, well, what multiplies to make that outside term negative 9 and then adds to make the 8? Well, what I would say is I would say, okay, we have a positive 9 and a negative 1. Positive 9, negative 1, because 9 times negative 1 is just negative 9, and 9 minus 1 is just 8. And then because we have a 1 as our coefficient of our x squared term, we can actually just write those as our factors. So x plus 9 and x minus 1 are the two factors. Okay, so let's highlight all the important information we just got from here. So we know that we're going to have to keep the x out front here. So this x that was out front, we're going to have to keep it out front here. So, and I'm just going to maintain that specific part by just keeping it in green. So we know that the x stays out front and we have our factor term. So we're going to carry this with us. That's our denominator. And then our numerator was this term where we just took the 9x off the two terms. So now let's rewrite our equation from above. We say our numerator was 9x with x plus 9 over, and then our denominator was x with x plus 9 and x minus 1. Okay, so what do we see that we can take off both? Well, right away I can see that we can cancel our x plus 9s. So our new equation becomes 9x over x minus 1. And now what's the last thing we can take off? Well, I also see that an x is in the numerator and denominator like that. So we know that we can take both of those off, and we should just be left with 9 over x minus 1. And therefore, that should be our final solution to this simplifying the rational expression. So in recap, what we had to do is we had to look at both the numerator and denominator and decide to take out a given greatest common factor, which we did for both of them. In the first one, we took off a 9x, and in the second one, we took off an x. And then we have to recognize, can we factor that further to simplify it? And in the second case, or in the denominator, we could factor that one. Then we had to resubstitute them back in for the numerator and denominator, and then just cancel them from there. So you should see how using greatest common factors and then factoring can allow us to simplify these by creating common terms in both the numerator and the denominator. All right, so I thought we'd go over this final problem just because I like the idea of focusing on what's in the denominator, because it does pop up a lot when you're dealing with rational expressions or other parts of math that you'll see down the road. But in rational expressions, this is one that we need to pay attention to. So like we did in both questions 5 and 6, we know that we're going to have to factor these in order to simplify them. So let's start with the numerator. We have x squared plus 3x minus 28. So we need something that's going to multiply to make the outside, which is 1 times negative 28, which is negative 28. What's going to add to make the inside, which is just 3. So what I would say is for both of these, we have, it should be a 7 and a -4, a 7 and a -4, because 7 times -4 should give us -28, and then 7 plus -4 should give us 3, so that works out. And then remember, if we have a 1 coefficient in front of our x squared term, then these automatically can become our two factors, and we don't have to do decomposition. Okay, now we want to deal with our denominator. Well, this is a special case we should recognize right away. In most cases of math, we call this a difference of squares. A difference of squares, in general terms, is written as a squared minus b squared is equal to a minus b, a plus b. So that's the specific thing we have right here. And in this case, what are our a's and b's? Our a is going to be this x squared term, and our b is the minus 49. And more specifically, we say x squared and minus 7 squared, because 7 squared is just 49. So now we say that if we want to write this in terms of a's and b's of our general term, well, a single a is just going to be x. A single b is just going to be equal to 7. And then yet again, a single a and a single b. So now we know that our difference of squares of x squared minus 49 is just going to give us this n term here, or this factor term. Now we can actually take both of those two that we solve for and plug them in for our numerator and denominator. So let's do that off to the side here. We have our numerator, which is x plus 7 and x minus 4, over our denominator, which was that difference of squares, was x minus 7, x plus 7. And then right away we should recognize, hey, look, there's something we can cancel. It's going to be the x plus 7s from both the numerator and denominator. Thus, our final term should just be x minus 4 over x minus 7. And we want to box that because that is our simplified rational expression. So just be careful when you see a term that looks like the one in the denominator where it's an x squared minus. I would always check to see if that number is a perfect square, because if that number is a perfect square, then we know we can use our difference of squares identity, which is just this one right here. And that will allow us to solve for the two factors that compose the denominator.